A mountain is a large landform that stretches above the surrounding land in a limited area, usually in the form of a peak. A mountain is generally steeper and bigger than a hill. Mountains are formed through tectonic forces or volcanism. These forces can locally rise the surface of the earth by over 3000 meters. Mountains erode slowly through the action of rivers, weather conditions and glaciers. A few mountains are isolated summits, but most occur in huge mountain ranges. The highest mountain on earth is Mount Everest in the Himalayas of Asia, whose summit is 29,035 feet above mean sea level. The highest known mountain on any planet in the solar system is Olympus Mons. This is on Mars at a height of 69,459 feet. There are 4 different types of mountains that have been recognized. They are volcanic mountains, folded mountains or fold belts, fault block or block faulted mountains, and erosional or upwarped mountains. The classification of the mountains is based on the factors such as the geometry, structure, rock composition and or age. These are indeed successive stages in the development of mountains. Besides being distinctive types, volcanic mountains represent the initial stage in the development of such gigantic landforms, while folded mountains represents the peak of youthfulness and maturity, and erosional or upwarped mountains represent the old age. Fault block mountains can be produced at any of these stages, but nevertheless have traditionally been treated as a specific type of mountain. These 4 types or stages in the development of mountains can briefly be described. Volcanic mountains. These are the simplest known mountains and are usually in the form of isolated peaks formed from accumulated lava flows, pyroclastic debris and other extruded igneous rocks that might have piled up rapidly, that is only a few years, or might have piled up over thousands or even millions of years, such as Kilimanjaro of East Africa, Paricutin of Mexico, Mauna Loa of Hawaii, Vesuvius of Italy, Fujiyama of Japan, etc. Such piling up of eruptive material can take place around volcanic vents producing cinder cones, such as Vesuvius near Naples in Italy or elsewhere, producing volcanic mountains. It can also flow out at the surface and consolidate in the form of a broad, gently sloping, flat-topped volcanic dome, usually several tens or hundreds of square kilometers in extent, being chiefly built of overlapping and interfingering basaltic lava flows, volcanic shield. These can gradually grow into volcanic mountains such as Mauna Loa in Hawaii, which rises from a depth of 4,270 meters below the sea level to a height of more than 3,960 meters above sea level. Kilauea of the same island and the great basaltic accumulations of Iceland. Volcanic mountains seem to have their origins connected to deep faults that extend below the Earth's crust to the mantle which supplies their building materials. In other words, volcanic mountains are directly related to deep faults in the Earth's crust and hence are considered to represent the earliest stage in the development of a mountainous chain. In terms of global tectonics, most of the volcanic types of mountains are believed to be associated with movements near the boundaries of lithospheric plate. These are created as a result of downward subplate disturbances, example the Aleutian and the Cascade volcanoes, or as a direct consequence to the pulling apart of lithospheric plates at mid-oceanic rifts, example both Kilimanjaro and the Kenya mountains which are both directly related to the East African rift system. Indeed, active volcanoes are most abundant in narrow belts, particularly in the island areas that rim the Pacific Ocean, where it is believed that the Earth's crust is currently being consumed by descending into the mantle, as well as along mid-oceanic ridges, where the new oceanic crust has been steadily produced since at least the time between 150 and 200 million years ago. The Aleutian Islands are peaks of volcanic mountains that stretch out for 3,200 kilometers along the circumference of a circle centered at 62 to 40 degree north latitude and 178 to 20 degree west longitude. Island arcs festoon the western borders of the Pacific Ocean with great oceanic deeps, that is trenches, on the outside curve of many of them. More than 64,000 kilometers of mid-oceanic ridges have so far been mapped around mid-ocean rift valleys. These have been pouring out fresh basaltic material on both sides of such ruptures in the Earth's crust since the early days of their initiation to build up new oceanic crusts. The youngest oceanic crust will always be around deep rift valleys and will steadily push older crusts away from it. The oldest existing oceanic crust does not exceed the Mesozoic in age and is currently being consumed at the convergent edges of the plates with rates almost equivalent to the rate of producing new oceanic crust. Few volcanic mountains are found on the continents, such as the isolated peaks of Ararat 5,100 meters, Etna 3,300 meters, Vesuvius 1,300 meters, Kilimanjaro 5,900 meters and Kenya 5,100 meters. These are also associated with intracratonic deep rift systems that communicate with the upper layer of the Earth's mantle. These represent the peak of the development of mountain belts and hence are represented by the great mountain systems of the world, such as the Himalayas, Alps, Andes, Carpathians, Urals, Juras, etc. Such mountain systems normally comprise broad belts of varied rock types and of structural patterns that involve folding, faulting, overthrusting and igneous activity. Faults are particularly numerous along the borders of these highly folded belts. Some are normal faults, but the majority is low angle thrust faults that extend for hundreds of kilometers, pushing gigantic masses of rock over one another for many kilometers, that is overthrusting. Field observations clearly indicate that the development of folded mountains was normally preceded by the formation of geosynclines. A geosyncline is a large basin in the Earth's crust, usually scores of kilometers wide and hundreds of kilometers long, with sediments of marine origin that do not usually exceed the 300 meters depth that alternate with layered volcanic accumulations in complexes of more than 15,000 meters thick. The sediments accumulated in a geosyncline eventually sink into levels where they become surrounded by denser, more viscous rocks, and their own buoyancy sets a limit to the depth to which they can sink under their own weight. At that point, the whole system becomes isostatic and the thickness of the sediments cannot be increased just by load. Both folding and faulting occur continuously while sediments are accumulating. Rocks at the surface are brittle and hence they break before they flow, but under deep burial they become plastic and change both their shape and volume by folding and are slow flowing. When sediments are buried deep enough, they melt. Expansion of such molten rocks causes the whole overlying mass to rise, and their cooling will produce basement rocks that often participate in the folding process. Near the edges of the geosyncline, the rocks are squeezed upward and outward along great thrust faults, while in the central area they are pushed upward to form an intermountain plateau. Evidence of pre-consolidation folding supports the contention that the mountain building forces were active during sedimentation. Indeed, differential downwarping could have produced folding while deposition was in progress, but at this stage the dominant forces were probably mainly vertical. Thrust faulting along the margins of the geosynclines could have been initiated by a bordering zone of differential subsidence, but as active horizontal and tangential compressive stresses are usually late in the geosyncline's history as a result of the collision of plates, they may be the main cause of overthrusting. Such stresses finally elevate the already deformed strata to mountainous heights. Modern examples of geosynclinal zones growing slowly into mountain ranges are thought to exist today between the Pacific border of Asia and arcs of volcanic islands off the continental coast. From the above mentioned discussion, it is obvious that the major mountain systems have evolved as a result of the movement of lithospheric plates. At the boundary of two such plates, one plate can move down relative to the other. A geosyncline develops, and island arcs are built by the piling up of eruptive volcanic material initiated by subduction. Later, the geosynclinal infilling of sedimentary and volcanic rocks rises to form a mountainous chain. As it rises, folds and faults develop either through squeezing, the horizontal tectonic hypothesis, or through gravity sliding of material away from the rising, the vertical tectonic hypothesis, or by both. Mountain ranges could also result from the collision of two continents being rafted along on their lithospheric conveyor belts, example the Alps and the Himalayas. In both the cases, folded mountain ranges were not formed by the deformation of only one geosyncline, but rather by the deformation of many. Present day mountain ranges were definitely much higher. These were worn down over time and were left as erosional remnants of the virginal, sharply folded and faulted uplifts. Isostatic rebounds for the whole mountain range would also intervene to compensate for erosion and keep the isostatic adjustments. This can go on until the mountain roots are exposed to the surface, attain the thickness of the surrounding lithosphere, and the mountain chain is almost completely leveled. These mountains are formed by uplift of the earth's crust along steep dipping or almost vertical faults. Differential tilting of blocks of the earth's crust along the areas of separation, such as rifts, can produce fault block or block faulted mountains. These occur in many parts of the world, frequently adjacent to incipient oceans, such as the Red Sea, or at the periphery of fold belts. Subsequent to folding and low angle thrust faulting in such belts, a period of steep block faulting produces fault block mountains at the periphery of the folded mountain range. Fault block mountains are large, uplifted sections of the earth's crust that are bounded by faults in the form of alternating horse and grabens. Example, the Great Basin and Range province of Oregon, the Sierra Nevada of California in United States of America, the mountain ranges that border both the Red Sea Rift and the rift valleys of East Africa, etc. Their rocks may be totally crystalline, igneous and metamorphic complexes, or may carry a thin or a thick sedimentary cover. The sedimentary cover, being originally deposited in a geosyncline, can sometimes be folded during an earlier cycle of deformation. Before the region was broken up into blocks and uplifted by successive movements along the different planes of faults over millions of years to attain mountainous heights. In the North American Cordillera, along the western border of North America, the fault block mountains began to be elevated about the same time as their neighboring folded mountains and plateaus, indicating that regional deformative forces were acting. Many geologists believe that the block faulting is due to either stretching or relaxation in the later phase of a geosyncline or mountain building cycle. But according to the theory of plate tectonics, large-scale rifting may be due to intraplate ruptures followed by the pulling apart of the ruptured lithospheric plate to diverge away from each other as two new separate plates, such as the splitting up of the Arabian or Nubian plate. Fault block mountains can also be produced at a later stage in the development of subdued folded mountains, when faulting can provide the necessary elevation of the mountainous range. The next type of mountain is the upwarped or erosional mountains. These are the erosional remnants of previously existing mountain ranges and owe their present heights appearances to broad upwarpings of the Earth's crust as a result of isostatic adjustment. Example: Ozarks, Adirondacks, Appalachians, Rockies, Black Hills, the highlands of Labrador, etc. When the old mountain chains were worn down by erosion and reduced to subdued topographies, isostatic readjustment brought them to their present day elevations. Such subdued elevations represent the final stage in the history of a mountainous chain before they are almost completely leveled and added to a previously existing craton. Mountains and climate. The position of mountains influences climate, such as rain or snow. When air masses move up and over mountains, the air cools, producing orographic precipitation, rain or snow. As the air descends on the leeward side, it warms again in accordance with the adiabatic lapse rate and is drier, having been stripped of much of its moisture. Often, a rain shadow will affect the leeward side of the range. A geyser is a spring characterized by intermittent discharge of water ejected turbulently and accompanied by a vapor phase, that is steam. The formation of geysers is due to particular hydrogeological conditions which exist in only a few places on the earth, so they are a fairly rare phenomenon. Generally, all geyser field sites are located near active volcanic areas, and the geyser effect is due to the proximity of magma. Generally, surface water works its way down to an average depth of around 2000 meters, where it contacts hot rocks. The resultant boiling of the pressurized water results in the geyser effect of hot water and steam spraying out of the geyser surface vent, a hydrothermal explosion. Over 1000 known geysers exist worldwide. A study that has completed in the year 2011 found that at least 1283 geysers have erupted in Yellowstone National Park, Wyoming in the United States, and an average of 465 geysers are active there in a given area. A geyser's eruptive activity may change or cease due to ongoing mineral deposition within the geyser plumbing, exchange of functions with the nearby hot springs, earthquake influences, and human intervention. Jet-like eruptions, often referred to as geysers, have been observed on several of the moons of the outer solar system. Due to the low ambient pressures, these eruptions consist of vapor without liquid. They are made more easily visible by particles of dust and ice carried aloft by the gas. Water vapor jets have been observed near the south pole of Saturn's moon Enceladus, while nitrogen eruptions have been observed on Neptune's moon Triton. There are also signs of carbon dioxide eruptions from the southern polar ice caps of Mars. In the latter two cases, instead of being driven by geothermal energy, the eruption seems to rely on solar heating via solid state greenhouse effect. Geyser eruptions. It is particularly interesting to think about why some of the geysers eject tall columns of water at regular intervals. What usually happens is that some groundwater circulates deep, often 1 kilometer or more, through the Earth's crust and becomes heated. This water travels up to a. In other types of pipes that do not have a constriction, the geyser does not become very tall because not much pressure builds up in the pipe. Although geysers are rare, they are important to geologists as geysers can indicate the location of heat sources below the surface of the earth. Also, studying the water from the geysers can tell much about the water that is circulating. A hot spring is a spring that is produced by the emergence of geothermally heated groundwater from the Earth's crust. There are geothermal hot springs in many locations all over the crust of the Earth. The water coming out from a hot spring is heated by geothermal heat, that is heat from the Earth's mantle. In general, the temperature of rocks within the Earth increases with depth. The rate of temperature increases with depth is known as the geothermal gradient. If water percolates deeply enough into the crust, it will be heated as it comes into contact with the hot rocks. The water from hot springs in non-volcanic areas is heated in this manner. In active volcanic zones such as Yellowstone National Park, water may be heated by coming into contact with magma, that is molten rock. The high temperature gradient near magma may cause water to be heated enough that it boils or becomes superheated. If the water becomes so hot that it builds steam pressure and erupts in a jet above the surface of the earth, it is called a geyser. If the water only reaches the surface in the form of a steam, it is called a fumarole. If the water is mixed with muddy and clay, it is called a mud pot. Hot springs in volcanic areas are often at or near the boiling point. People have been seriously burned and even killed by accidentally or intentionally entering these springs. Warm springs are sometimes the result of hot and cold springs mixing, but may also occur outside of volcanic areas, such as warm springs of Georgia, frequented for its therapeutic effects by paraplegic US President Franklin D. Roosevelt, who built the Little White House there. The geysers and hot springs are found in India. There are more than 16 natural geysers or hot springs in India. The examples are Vajreshwari in Maharashtra, Garampani in Assam, Manikaran in Himachal Pradesh, Puttur in Karnataka, Suryakunda in Bihar, Taptapani in Orissa, Bakreshwar in West Bengal, Tulsi Shyam in Gujarat. In some of the countries, geysers and hot springs are not just beauty spots. On the other hand, they are emerging as tourist spots and health cares.